Ready for the next problem now. We have a diffraction grating. This is a long one, so I might have to break this up into a few pieces. We start out with a diffraction grating. It's picket fences. The distance between openings is 1.5 micrometers. There we go. Instant light, wavelength 590 nanometers. And we want to know the orders of diffraction. Remember that when, here's D, here's the rays coming off, when this is some multiple of the number of wavelengths, this side here is some multiple of the number of wavelengths, it will be reinforced. This is the central beam, this is theta. It's pretty easy to show that this angle right up here is also theta, and so m lambda equals d sine theta. And you might have several. So I'm going to pause a moment for calculations. Theta 1 equals, theta 2 equals. You might have many more, so I'll be right back. Okay, I'm back. I got the first spot, you'll see at 23.2 degrees. The second spot, you'll see at 51.9 degrees, keeping 3 sig figs. You won't see a third one. You can only go up so far, depending on the wavelength of light and the size of the openings. Okay, that's part A, all the angles of the interference fringes. Part B, easy. You've got two orders. Now, instead of a grating like this, you have only two small slits, and you want to know what is the formula for intensity there, where the intensity through one opening is this much, I sub O. The ratio of the you want to know the ratio at the first diffraction spot. You'll actually have two, the same spacing, just like a grating. You'll have two, but it's much more spread out. As you'll recall, these are very sharp peaks. You have, if you plot it versus angle, you have very sharp peak, very sharp peaks. Whereas with two slits, it's spread out. It goes kind of like this. Okay. So the formula is 4 cosine squared of the phase angle over 2. And the phase angle, let's draw the picture again, at some angle theta. Well, the phase angle is going to be however many radians in phase does the wave change going from here to here. And this might not necessarily be at a peak. This is just some arbitrary angle theta. So from before, you get this distance is d, the spacing, sine theta. So d sine theta, that's the distance. The fraction of a total circle is this. You take d sine theta divided by the wavelength. That tells you what fraction of a full cycle you're at. If d sine theta equals lambda over 2. If theta is such that d sine theta is lambda over 2. You'll have a phase angle of 180 degrees. And then finally, you have to multiply it by 2 pi. There's 2 pi radians per cycle. So now this equals the phase angle. And stopping just a moment for calculations, I'll be right back. This answer is actually quite easy when you think about it. That at the first order diffraction spot, you're at this condition where m equals 1. So d sine theta over lambda equals 1. This factor right here is just 1. So the phase angle just equals 2 pi. Substitute 2 pi in there. What's the cosine squared of pi? 1. So this answer is actually pretty easy. Write down the formula. Remember, we have an intensity. Well, let's plot this. I sub O is the intensity at one of the at the center. Excuse me, not in the center. At one of the spots. So we're going to get a curve that looks something like this here as we go across. And then this is 4 high. The total intensity, so the total intensity on the slits, I naught is the intensity on one slit. Total is going to be 2 I naught. Well, but the peak is at 4. The center is 4 times higher than the intensity on 1. The first diffraction order is 4 times higher than the intensity on 1, and so forth. But what you're doing is you're averaging the cosine squared function. When you average that function, you get 1/2. So 1/2 times 4 is 2. Everything works out. We're not gaining or losing energy. Okay, let's go on to part D. And we're going to change this a bit. And we're going to make the spots finite size. So this assumes infinitely small spots, or infinitely small openings. Now we're going to actually change the openings, and that is supposed to be nanometers right here. NMs, not, or no, it's not nanometers, it's micrometers. That is supposed to be 0.2 of a micrometer. So you have two openings, like so, and this is 0.2. And the spacing is still 1.5 micrometers, and the wavelength of light hasn't changed. Okay. What you do is you take the intensity for the for a single opening, which we have our formula, I equals I in the center, IM, sine alpha over alpha. We proved this in class. We showed this proof in class, squared, where alpha is pi a over lambda sine theta. Okay. I think I better pause a second and do some erasing of previous work so that we can get back to this. I do want to be sure and hold on to this, because you multiply this result here, you multiply the two results together to get your final, when you have two openings. Here's finite opening. This is for one finite opening. This formula here is for one finite opening. When you have two finite openings, you just multiply this times this. I'll be right back after doing some erasing and write down our formula. Okay, I'm back. We're going to, now the formula, I over Im equals cosine squared. Halliday and Resnick calls it a new variable. It is no different than phi over 2. So instead of, anyway, they call it beta. I'll stick with the book's nomenclature, and you can tell that it's identical to what we had before. So that's double slit. Let's see, yeah, that's 2 slits. We're on part D right now. And we just have to crunch numbers. Alpha is given here. Beta is phi over 2, 2 pi d sine theta over 2 lambda. Well, 2's cancel out. And that's what beta is. It's phi over 2. And now we just crunch numbers, where this is the first diffraction spot. Sine theta is d. This factor will be 1. Sine of pi, of course, is 0. But the limit, well, anyway, we're going to find out. Oops, beta, let's see, beta is fine, alpha, good. And we're going to find out what this looks like. Just a comment before I go further. A is smaller than D. So alpha is going to change several times, while beta is going to change once. So alpha So as you move the angle, you have to move to much larger angles for alpha. Theta has to be big to make a big change in alpha, because A is small. So what you're going to get from a single slit, what you get is this. You get kind of a pattern that looks like this. And from the spacing, the D, the fact that the spacing between openings is larger, you're going to get this going on inside. So you're going to get a pattern that looks something like this here. Okay. Time to crunch numbers. I will be right back as soon as I do that. And I'll also, in the meantime, I'll also erase this picture. First we have alpha 0.419. Just like before, just like down in this problem here, phi over 2 is pi. At the first order of diffraction, phi over 2 is pi. So this actually, cosine squared of 1 is 1. So we're fine there. We're actually going to find sine alpha over alpha now. Okay, I got sine alpha over alpha equals 0.971. Does that make sense? That's pretty good, actually. This is a fraction of a radian. Of course, it makes sense. And then we square it. So sine alpha over alpha is 0.943. Oops, I went back to Panopto by accident. Okay, and that's the answer. Remembering we're at the first order of diffraction, 23.2 degrees. Also, be careful here. You've got to set your calculator to radian mode for this. Don't forget to do that. We've been working in degrees. So radian mode here, degree mode here. Be careful about this. Be careful. Okie dokie. Now, we're on to part E. We want gratings with 10 openings, and it's the same problem. Gratings, except there's 10 of them instead of just 2. Okay, I'll be back in just a second here. I'm going to clean things up. Okay, I'm back. We want, what is the half width of the first order diffraction? So that's 23.2 degrees, which we got before. I'm not going to rewrite it down until I need to, actually. Actually, I do need to do it. 23.2 degrees equals the angle where we get the first maximum. And the half width of a line is given by this formula. Wavelength over number of lines, that's 10 in this case, d cosine theta. And we just have to crunch. Let's see. All it asks for is a half length. Is the half width, excuse me. So this is just number crunching. This is part E. Oops. Come on. There we go. Be back in a minute after number crunching. Okay, I get an answer of 0.048, or excuse me, 0.428. Radians, not degrees. There's pi radian, there's 180 degrees per pi radians. So multiplying this by 180 over pi, I get 2.45 degrees. Watch out. We're working with things now where we're dealing with both radians and degrees. Dispersion. Basically, that tells us how accurately we can measure the wavelength. This is part F now. If we have a grating with certain properties, what is it? And it's defined as the change in angle divided by the change in wavelength. Angle in radians this time, radians. And it is just the mth spot. In this case, we're going to use 1, the first spot, and over d cosine theta. Be back after calculations. And I get an answer of 7.25 times 10 to the negative 4th radians per nanometer. Okay, Fg, resolving power. Basically, the bigger the better on this parameter here. That's the average wavelength divided by this delta lambda. So if we take this delta theta to be the half width, how accurately can we measure wavelength? And how is that compared to the average wavelength? That's what this resolving power is all about. So I'll be back after calculations. Oh, I forgot to write down the formula for a number of openings. In this case, 10 times m. M in this case is 1. Oh, well, gee, I can figure this one out. 10. H, let's see, we got the resolving power. H, this is Bragg diffraction, a little bit different. We have planes in a crystal. We have a beam coming in, and we have a beam coming in at the top, and beams going out. And when the path length difference, which is given by the sum of these two lines, When that path length difference is a full wavelength, then we get Bragg diffraction. This is the angle. Well, I know why they don't measure it from the normal, because your instrumentation, when you actually build an X-ray diffraction instrument, this angle makes much more sense. Normally, we measure angles from the normal, not in this case. So, when you write down this is the angle, well, the angle theta is right here. Here it is here, here it is here. And we get there we go. These are all thetas, those little angles I marked. And it's pretty easy to figure out. The spacing between planes is d. And we are going to get d sine theta twice. D sine theta, this is easy to prove, will equal m lambda. And the question here is, if d is 0.143 nanometer, a fraction of a nanometer, typical for crystallography, and m equals 1, so what does and sine of theta can be 9, sine of theta is also 1. What is the maximum wavelength? So we make wavelength bigger, we make sine of theta bigger. So what is the maximum wavelength we need to cause Bragg diffraction? And that would be these conditions here. Solving for wavelength, 2d sine theta, crunch the numbers. I'll be right back. I forgot sine theta is 1, so it's just 2d. And that's not too hard to figure out. 0.286 nanometers. I didn't even have to leave to go crunch the numbers. So that's it. Part H. We're done with this problem. See you on the next problem.